Hello, my name is Kyle Bursler, and this project is titled Caption This Presentation. At the bottom, you'll begin to see text flow onto the screen, and hopefully what it will do is as I continue to talk, it will start to catch up to where I have been talking since the start and start to accurately transcribe me. This is my project actively taking my streaming audio and converting it into text at the bottom of the screen. Before we dive in, though, a little bit about me and my motivation. I am a data scientist, bioethicist, philosopher. I have a PhD from Florida State University, and it's in philosophy. I'm still in the Tallahassee area. And the reason I wanted to do this project is because I heard a very interesting story once about someone who received a cancer diagnosis. And after receiving the diagnosis and hearing the word cancer, they did not hear anything else that the doctor said. So they walked away from that visit not being able to really take any of the doctor's advice or notes with them. And so this is a kind of technology that can really assist in that kind of situation. Perhaps this kind of technology could capture what the doctor said and highlight important things that were given to the patient verbally, and then give them some kind of a document to walk home with that has important highlights from what the doctor said. And you can imagine there's also numerous other highlights in healthcare and other places, other industries. So the project was to learn how to featureize audio data and build a pipeline that could caption speech on the fly and run on something very lightweight, such as my own pitiful laptop. So featureizing needs to be fast so that it can keep up with the incoming audio. And the model that I use needs to be lightweight so that it can actually run quickly. So a couple of different approaches. I could either go character level, phoneme level, or word level. As they all sound, they're pretty obvious what they're doing, but I decided to start with the word level approach first. So my first model is a pretty simple one. I ran this model on the Google Speech Commands dataset. It's basically just a pre-labeled data set with about 30 different commands, but I only used 10 of them. I resampled my data and I just ran the model through on raw audio data, and has 4 1D convolutional layers. And this actually did quite well. So this reached 86% accuracy on the 10 basic speech commands. And when I recorded myself saying them, it picked up on every one of them accurately. So with this booming success, I decided to move on to the next model, a more advanced word model. This example on the right is not my actual model, but it is an example of what I used. I just made it more deep. This right here is a bidirectional LSTM layer, and I had 4 of these and tried to use this to achieve something like a state-of-the-art capturing of my words. But unfortunately, I could never get above about 20% accuracy. I ran this on the LibreSpeech dataset, lots and lots of data, but unfortunately, it did not do that well. So essentially, I realized that the word approach was probably going to be difficult because in this process of training, I was doing some reading and found out that a good model will take approximately 30 days to train when you're using a large enough data set. So maybe this would have eventually done better, but for my purposes, it's hard to see here, but I never got below about 40 on my loss, and that's just not good enough. So I went back to a more traditional approach. I had already done the raw audio processing. I added in some feature extraction with spectrograms, and I used a lightweight pre-trained model, and then learned how to build a decoder for character level predictions. Part of that decoding process includes using CTC loss, which is connectionist temporal classification. This essentially takes strings of characters and compresses them using probabilities into the most likely text for them to be. And then also it couples that with a language model in order to use n-grams to try to get the best probability of what you're actually trying to say. So coupling that with my shallow model, it was a 5-layer model, just a couple of dense layers, an LSTM, and then a dense output. As I said, I used some spectrograms and I made them all single channel. But the one thing that's interesting is I augmented my data set by using time and frequency masking. So this essentially cuts out sections of the spectrograms so that the network can be more robust. Credit to this pre-trained model goes to Michael Fye. You can check out his YouTube. I also trained his model I fine-tuned it on my own voice. I took about an hour's worth of wave files in my own voice through Mimic Recording Studio, very neat tool to use, and trained it for 25 epochs and reached a loss of 0.22. And essentially, this makes it so that the model can more accurately distinguish my voice. And you can see here how it did. Even though it looks like it could get a little better with more training, I did about 200 epochs. This was about where 25 ended. And this was the best that it got over 200 epochs. So as you can tell from the bottom, my network is actually working pretty well. Not perfectly, obviously. So one thing to do is to improve the model. So I would like to train it on more data. Also maybe implement this on a mobile device so that the application I mentioned at the start would be possible. And then there's new research or new-ish research on combining word and character approaches. And so I'd like to perhaps implement some of that to try to also push the model to the next level. Thank you so much for watching my presentation. I hope you've enjoyed it. And if you need to reach out to me or would like to talk about any of this, here's my contact info. Thanks.